In this video, we're going to talk about limiting and excess reactants, which is an extension of our stoichiometry topic. These are your learning targets. Now let's think about the words limiting and excess reactant. You guys have actually heard of these words before, right? So let's start off with an example. And we are building cars and we are given 8 car bodies. Each car needs 4 tires. If we're given 48 tires, how many cars could we make? We could make 8 cars. So if we made 8 cars and each car takes 4 tires, how many tires did we use? We used 32 tires. So how much is left over? Right, 16 tires are left over. So let's first think about these words limiting and excess reactant. First of all, we're talking about reactants, so we're really just focusing on the left side of our equation, the left side of the arrow, right? And so here we have 2 reactants. One of them is completely used up, the other one has extra. Now think about the words limiting and excess. Excess, you guys know, means extra. So what is in excess? The tires are in excess. So we say that the tires are the excess reactant in this case, and our 8 car bodies is our limiting reactant, right? We could only make 8 cars. We were limited to how many car bodies we were given. And so once that ran out, we couldn't make any more. So the limiting reactant is the reactant in a chemical reaction that limits the amount of product that can be formed. The reaction stops when all of the limiting reactant is used up, and it determines the amount of product that is made from our reaction. The excess reactant is added to make sure the other reactant is completely used up. It will remain in the reaction, and it's not going to react with anything because there's nothing with which it can react with. So instead of using cars, now let's take a look at atoms and molecules. So remember that the coefficients, what we learned before, the coefficients in front of the substance tells us the number of moles, right? So in this case, we need 2 moles of hydrogen and 1 mole of oxygen in order to make 2 moles of water. So if we're looking at this picture, how many moles of hydrogen do we have? We have 10. How about oxygen? We have 3. So how many water molecules can we produce? Now, some of you guys may need to draw it out. And so we need 1 oxygen and 2 hydrogens. You guys learned in biology that it's like the Mickey Mouse ears, right? So go ahead and draw that on your paper. You can cross it out as you keep drawing. Okay? And how many water molecules could you make? You can make 6 moles of water. So what is left over? And how many moles are left over? Right, you have hydrogen left over, and you should have had 4 moles of hydrogen left over. So in this case, what is our limiting reactant? What was used up first? The oxygen. And then what we had left over, what we had extra of, what was in excess is hydrogen, H2. So in order to solve these problems, there's really only 2 steps. Step 1 is for each reactant, we're going to calculate the amount of product formed. And step 2, the smaller answer will tell us the limiting reactant and the amount of product that is formed. So let's jump in to example A. So we have this reaction, carbon monoxide and oxygen produce carbon dioxide. And we are given 12 moles of carbon monoxide and 7 moles of oxygen, and it wants to know how many moles of carbon dioxide we have. All right, so we're going to go ahead and write those down. And if you take a look at this problem, how is this different from what we learned in stoichiometry? You have 2 givens, right? Whereas in stoichiometry, we only had 1 given, and we were trying to find, we had 1 desired product. So we need to figure out, well, how much product can be made. So I'm going to pull up this picture again because we're still doing stoichiometry, right? And we want to go ahead and match up the units. So since we're given moles for this one, we want to start at mole of A. So I'm going to go ahead and cover that up. And where do we want to stop? We want to stop at moles of B. Okay, so let's go ahead and set up our first part of the problem. We are going to start with 12 moles of carbon monoxide. So let's set up the top part of the fence. So we need moles of carbon dioxide on top, and we are going to replace that with the fence. Copy down the unit, moles of CO. And remember what this is, moles of one thing over moles of another. It's the molar ratio, right? And where do we find the molar ratio? We're looking at the coefficients of our balanced reaction. So we have 2 to 2. 2 moles of carbon dioxide to 2 moles of carbon monoxide. Like units cancel out, multiply 12 times 2 divided by 2 is equal to 12 moles of carbon dioxide. Now, we're going to do this again, except this time we're going to start with 7 moles of oxygen. And we still want to go through the same thing, right? So from moles of oxygen, we're going to go into moles of carbon dioxide, replace that with the fence, bring down the unit, moles of O2. And what is the ratio for this one? 2 moles of carbon dioxide is to 2 moles of carbon dioxide to 1 mole of oxygen. So multiply and divide, and we get 14 moles of carbon dioxide. All right, great. We set it up twice. We have 2 answers. Now we're looking at the smaller answer. So out of these two, what's the smaller answer? It's 12 moles of carbon dioxide. So that is how much is produced, 12 moles of carbon dioxide. So what is our limiting reactant? The reactant that runs out first then is carbon monoxide. This is what this is telling us, right? So what is in excess? O2 is in excess. All right, that's what's left over. All right, if we take a look at the next example, similar problem, except this one is a mass to mass, grams to grams kind of problem. So let's write down what we're given. We're given 100 grams of aluminum and 100 grams of chlorine, and it wants grams of aluminum chloride. So we're going to use this entire picture, right? We're starting at grams, ending at grams. So we're starting with 100 grams of aluminum, going into moles of aluminum, and then moles of aluminum chloride, and then grams of aluminum chloride. Going to replace all that with the fence. Copy down your units, grams Al, moles of aluminum, moles of aluminum chloride. And now let's fill it in with numbers. So moles over G, what is that? Molar mass. Look on your periodic table, and we see that 1 mole is equal to 26.98 grams of aluminum. Next one is a molar ratio. We have a ratio of 2 to 2. And last one, molar mass of aluminum chloride. Go ahead and pause the video if you need to so that you can figure out the molar mass on your own, right? And we get 1 mole of aluminum chloride is equal to 133.33 grams of aluminum chloride. Multiply all that and divide. Again, pause the video so that you can do the work. And you get an answer of 494 grams of aluminum chloride. Let's do this again. We're going to start with 100 grams of chlorine, going into moles of chlorine, going into moles of aluminum chloride, and going into grams of aluminum chloride. Replace all that with the fence. Go ahead and pause the video here so that you can fill in the rest of the fence. I'm going to copy down the unit, grams chlorine, moles of chlorine, moles of aluminum chloride. Let's fill it in with numbers. Molar mass of chlorine is 70.90, a ratio of 2 to 3. And again, it's the same molar mass for aluminum chloride, right? And multiply and divide, and we get a total of 125 grams of aluminum chloride. So, what is our final answer? Our final answer is 125 grams of aluminum chloride. That is how much will be produced. That means the limiting reactant is chlorine, Cl2, and aluminum will be in excess. Now, the next part on this problem, it says how excess reactant will remain. Well, remember what we ended with. We can only produce 125 grams of aluminum chloride. So what the other question is asking about is, well, we started with 100 grams of aluminum. How much of this will be left over? So what you want to do is you want to start with your limiting reactant. Now remember, stoichiometry, you can determine how much of anything you might need or how much you need to produce, right? And so we're going to start with our limiting reactant, 100 grams of chlorine, and we want to figure out how much aluminum we actually needed, okay? So starting with 100 grams of chlorine, and we're going to go all the way to mass of aluminum because what they're giving us is also mass of aluminum, right? So 100 grams of chlorine, 2 moles of chlorine, into moles of aluminum, into grams of aluminum. All right, and then replace that with the fence, copy down your units, and then molar mass, molar ratio, and again molar mass. Multiply and divide, and you get a mass of 25.4 grams of aluminum. So this means that only 25.4 grams of aluminum was actually needed and was actually used in this reaction. So knowing that we only needed 25.4 grams and we actually put in 100 grams of aluminum, how much is actually left over? So how do you solve this problem? All you do is simply subtract. 100 grams minus 25.4 grams is equal to 74.7 grams that remain. Now some of you guys might be thinking, well, can't we just add and subtract? Why did we have to do all this fence? Because isn't that what law of conservation of mass is all about? So you can't just add and subtract, because if you take a look here, for this particular problem, this is a synthesis reaction, right? So yes, you would only get one product, but what if you had two products? You're not given the mass of your other product, so you can't do that. You can't just add and subtract. You have to do all this in order to get to the final answer. So go ahead and try the next example on your own. So pause the video, and when you're ready, you can go ahead and play it, because the next thing that's going to pop up are the answers. You should only be able to produce 113 grams of water, and how much of the excess reactant will remain? 37.3 grams of hydrogen.